Hi, Year 11s, this is Mr. Lim here again, and this is our, sixth video on atomic structure about flame tests and atomic emission spectroscopy. Let's get to it. This is what we're going to be learning about today, about flame tests, about electrons and what they do, and atomic emission spectrograms. Okay, so let's get on. Electrons and energy. So let's have a look. Electrons around an atom will naturally move into positions in orbitals which are close to the nucleus as possible. So they move into positions in orbitals. They don't stay stationary. They kind of move within those regions of space in those orbitals. And the important thing is that they are as close to the nucleus as possible. Okay, and this is called their ground state. So, just in everyday life, they're in this ground state where all the electrons are close to the nucleus as possible. If the electrons are given energy, they can move into higher energy levels, which means that to be in a higher energy level, it's not its normal state, it's not its ground state. They need to have energy, so when they're given energy, they move up those energy levels. They don't stay in those higher energy levels because they're unstable, and this is called the excited state. And when they're unstable, they will come back down at some point, but the types of energies that they can use, there are many different types of energies to help them move higher, such as heat, electricity, or light. Okay, once they're in the excited state, they don't stay there for very long, so when they return to their original energy levels, they release energy, because they gained energy to get there, in the form of light. And that's the important idea. Light is what they emit. Okay, so flame test is an example of that. So if a sample of a metallic element, which is generally powdered or in a solution, is heated in a flame, the electrons that are in that sample can accept the energy from the flame and then move into higher energy levels. Okay, so they get the heat from the fire and they move into higher energy levels. When they return to their ground state, which is almost instantaneously, so they effectively go up the energy level and then they go back down, they release the energy absorbed in the form of light. So it went in as heat energy and it comes out as light energy, right? Different metals will release different wavelengths of light. Okay, so different metals will release different wavelengths of light and thus produce a different colored flame, okay? Which can be used as qualitative data, which means it's a quality of the product, whether it's red or blue or whatever, to identify the metal present. Okay, so when it goes up and then it comes down, it releases energy, and that energy might be in the form of blue light, it might be in the form of green light, it might be a form of yellow light, or hell, it could be a combination of all three, blue, yellow, and green lights. Okay, but when the electrons come down back to their ground state, that's when they release their energy. All right. What is atomic emission spectroscopy then? Right, so atomic emission spectroscopy is a sample of an element, is heated sufficiently to provide it with sufficient energy or electrical energy. So you provide it with different types of energies. It can absorb that energy and cause the electrons to move up to higher energy levels. We knew that. It will release that energy in the form of light. We knew that. And that light is often a combination of different wavelengths. Okay, so not only is it releasing the blue light, but it's also releasing green light and yellow light, just like how magenta is a combination of blue and red light. Okay, so when it releases that combination of the different lights, so remember it goes up, then it comes down, then combination of those three colored lights. Okay, those combination of three colored lights are, so small that they all kind of end up looking like one color. But if you were to separate them out using a prism, and you can kind of separate out those things like a prism separates out a rainbow colors, you will see that only a few specific wavelengths, so you use a prism to separate the wavelengths, you'll see that only a few specific wavelengths of light are present within the combination of light. Okay, so you're only going to get blue, green, and yellow, and not bluey green, and not red or orange or those other colors, right? So, that's not what I wanted to do, all right? Okay, this representation of the wavelengths present in a sample emitted is called an atomic emission spectrum, and this is called qualitative data, okay? So what it will look like is this, all right? So first of all, when you spread out that light, here, you'll generally shine it onto something, okay, and generally shine it onto something dark, Okay, so in a dark room, then what you're going to see is a band of blue light will be there, a band of green light will be here, and a band of yellow light will be there, and the rest of it will all be dark. Okay, so all black everywhere else. Okay, and so what that's showing is that that one there is emitting those three colored lights. All right, so that thing here is called the AES, where the S stands for spectrum, atomic emission spectrum, and it's qualitative data because when you see those three lines there, that's characteristic for that particular sample or that element. All right, each element, that's not what I wanted. Each element will have their own specific combination of emitted light and produce a characteristic combination of light, which means that they'll look different colors. So this might be one particular sample above with the blue, green, and yellow. But say I take another sample and I split that via a prism over here, and maybe it's got a combination of red and blue light only. All right. When you put those through a prism, those will disperse a bit, and the AES that you'll see will only have a red line and a blue line. Okay, and the rest of it will be black again. Okay, so that's what you'll see for a different sample. Okay. And if you were to look at these particular things, if this was an unknown sample, right? If this was an unknown sample, and you were to look at this and you see this particular red and blue pattern, you could compare it against all the ones that we already know and be like, well, we know all of these ones and it matches this particular element, so therefore we know this sample has that particular element. All right. If the sample contains more than one element, then the wavelengths of both or all of the elements will combine and be shown on the spectrum. Okay, so we've just had two samples here, all right? One producing blue, green, and yellow, and another producing red and blue, all right? So if we were to have a sample with both of those things, it would have red light, it would have red light going through it, blue light going through it, green light in it, and yellow light, okay? And then when we were to draw the spectrum, right, we would see the red light, then because we're just sticking in order, the blue light, the green light, and the yellow light, okay? And maybe you'll see another blue light over here because otherwise it doesn't make sense in the thing, all right? So what that would look like, remember everything else is blackened out, okay? Everything else is blackened out. So what you would be able to do is you'd be able to compare it to your two samples. We have sample A and sample B, where A had the blue, the green, and the yellow, and everything else was blacked out. All right, and the other one had the red and the blue, okay? And so what you would be able to see is that everything else is blacked out there as well, okay? So what you would be able to see is that, okay, well, see this line here, that matches up with that one. This red line matches up with this one. This blue line matches up with that one. This green line matches up with this one. And this yellow line matches up with that one. All right, so you would say that this sample has both A and B, okay? Because it's showing all of the lines of both its component of those two particular samples, right? So that's what we mean by each element produces its own specific combinations, and if you have a sample of more than one element, the wavelengths of all those will combine and be shown on the spectrum, all right? And this produces you qualitative data, which means that you can use it to identify stuff because they are unique in their characteristic wavelengths released. All right, and that's all. We'll be doing some questions about this in class. If you have any questions, come and ask me. Adios.